Okay, so the camera is working now. So the first half of this lecture wasn't recorded, but you can get it from the morning class. But let's go back to bicarbonate. Looking at that. HCO3 minus. I'm just going to follow the steps here. Step 1, count the total number of valence electrons just for charged ions. So hydrogen had 1 electron, carbon has 4 valence electrons, 3 oxygens, each oxygen is 6, so there's 3 times 6 electrons, which will give us 18. And then the -1 charge, the -1 is an extra electron is going to give us a negative charge. And that's 5, 18, it's 23, 24 electrons total. Place the least electronegative atom. Least electronegative is hydrogen, but hydrogen only forms 1 bond, so we'll throw in carbon in the middle. And then let's attach the oxygens. We have 3 oxygens and 1 hydrogen. Draw something like that. Draw the tentative diagram, join atoms by single bond. So this is my tentative diagram here. Add unshared pairs to complete the octet around all atoms except hydrogen. Okay, so let's do that. I'll need 3 lone pairs here. 3 lone pairs there. So now I've completed the octet around all the atoms, and carbon has an octet. If I look at the total number surrounding it, it's 2, 4, 6, 8 electrons. And then each oxygen, 2, 4, 6, 8. It's a win-win type situation where we can double count the shared electrons. Step 4, calculate the number of valence electrons in tentative diagram and compare it with the actual. And so what we're going to do is we're just going to count the number of electrons in our Lewis structure and then compare it to how many we're supposed to have. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have 26 electrons in this. And so that's too many electrons because I only have 24. I'm supposed to only have 24, and I got 26. And so somebody has to lose. Somebody has to lose 2 electrons, so who can lose? It's got to be one of the 3 oxygens. You know, I can't take a bonding pair out, otherwise it becomes disconnected, so let's remove that. And so now I have 24 electrons here, if I remove that pair. But one thing's happened, and that is I no longer have an octet. So remove a lone pair. It's either from a central or terminal atom. There's actually 2 sentences here. And we'll replace with an additional bonding pair. In other words, what we're going to do is we're going to make sure that the number of electrons match. Now, if we don't have an octet, what we can try to do is form a multiple bond. And so what we can do is we can convert a lone pair into a bonding pair like that. But if we convert a lone pair into a bonding pair, does it change the fact that we don't have an octet? Yeah, we still don't have an octet around that oxygen, and there's one additional problem. We're going to have more than an octet around carbon. So if you look around carbon, we've got 2, 4, 6, 8, 10. 10, it only takes 8 electrons to fill up the shell. Those extra 2 electrons are going to go in the next higher energy shell, which is unstable, it's destabilizing. So we don't want to do that. And so is there any way to make an octet around this oxygen here that you can think of? No. This is pretty much a dead-end structure. We can't go with that. And so we have to figure out a different skeleton. And so one skeleton that we can come up with like this. Where we'll, rather than put the hydrogen on the carbon, we'll put the hydrogen on the oxygen. All right, and that is because of this. Bicarbonate comes from carbonic acid. Carbonic acid, are both these hydrogens acidic or is just one of them acidic? In carbonic acid, both of these are acidic. So if we lose one of those hydrogens, we have to form bicarbonate. Bicarbonate could either be an acid or it could be a base. So it could lose that additional hydrogen as an acidic hydrogen, or it could gain one to form carbonic acid. And so bicarbonate is what we call an acid anion. And therefore, the hydrogen should not be bonded to carbon, because if the hydrogen were bonded to carbon, what do we call that kind of bond? A hydrogen-carbon bond is called a, what type? Non-polar covalent, polar covalent, or ionic? It's a non-polar covalent bond, and this is not going to make an acidic hydrogen. This is going to be a non-acidic hydrogen. This electronegativity difference is only 0.4. Carbon's at 2.6, hydrogen is at 2.2, it's only 0.4, which is negligible. Whereas over here, if hydrogen is bonded to oxygen, then that's a more significant delta E of 1.2. This is going to be a much more polar bond, making this hydrogen much more positive. In other words, it's going to be much more acidic. And so for an acid anion like this, we always put the hydrogens on the most electronegative. Not just acid anions, but any acid. In any acid, if we have an acidic hydrogen, we put it on the most electronegative. Yeah. This is why it's something like acetic acid. Acetic acid has 4 hydrogens, but only one of those is acidic. The other 3 are bonded to carbon. Okay, so what we're going to do is we're going to complete the octets to everything. So if we complete the octets to everything, this is what we get. But let's do our electron count. When we do our electron count, we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I still have that problem. This is too many electrons. And so I need to remove 2. Now I have a choice. Should I take the 2 from oxygen, or should I take the 2 from carbon? Which one will give me more resistance or less resistance? Actually, I want the one that gives me the least amount of resistance. Should I take them off oxygen, or should I take them off carbon? Which one would resist the least? And so it'd be the easiest to pull 2 electrons off carbon, or easier to pull 2 electrons off oxygen? Carbon. Why carbon? It's easier to pull them off carbon because carbon is less electronegative. Carbon's a bigger atom, oxygen's a smaller atom. Carbon's easier. But if I take those 2 electrons off carbon, it leaves me without an octet. And so this is the second part of this. The sentence is very confusing. They should actually break it up. If the diagram has more removed. So I removed the lone pair from the central atom. And so what I'm going to do is I'm going to take a lone pair off one of the terminal atoms and make a double bond. So what I'll do is I'll take a pair and bring them over here. So I'm going to end up with a structure that looks like this. Now, take a look. Oxygen still has an octet. 2, 4, 6, 8. 2, 4, 6, 8. So oxygen still has an octet, even though it donated. But what that did was it helped carbon. If you look at carbon now, carbon has an octet. And so it's good. Everybody has an octet, and then hydrogen has a duet. So this is what our first priority is. Our first goal is to get an octet around each atom. Okay, when we draw Lewis structures like this, we also do the formal charge. We always show the non-zero formal charges. And so let's count the formal charges here. What's the formal charge around this oxygen? The formal charge around the oxygen depends on how I divide the bonding electrons. Do Do I split the bonding electrons down the middle, or is it winner take all? Formal charge. Split it down the middle, or winner take all? Split it down the middle. And so if I split this down the middle, this is what's going to happen. I got 1, 2, 3, 4. These aren't shared. So those belong entirely to oxygen. But now I have this double bond. A double bond consists of 4 electrons, 2 from the first line, 2 from the second line. And so out of the 4 electrons in the double bond, 2 go to the oxygen, the other 2 go to carbon. And so I'll count it 2, 4, 5, 6. So this oxygen ended up with 6 electrons. How many did the oxygen contribute? 6. So it broke even. It contributed 6 electrons. It ended up with 6 electrons, so it neither gained nor lost. It came out with 0. Let's go on to carbon. I do the same thing. Each bond is split down the middle, and then figure out how many electrons belong to carbon. So how many electrons do you count for carbon? Yeah, 4 is correct. We split it down the middle, we're going to get 1, 2, 3, 4. How many did carbon contribute? Carbon contributed 4 valence electrons, so it contributed 4, it ends up with 4, it broke even. Let's go to this oxygen over here. This oxygen. How many do you count for that oxygen? 6. And it contributed 6, so this oxygen broke even, it's 0. This hydrogen contributed 1. It ends up with how many? 1, so broke even. This oxygen up here, yeah, 7. So that oxygen up there has 7, but it only contributed 6. So it came out ahead, 1 extra electron. If it comes out ahead 1 extra electron, the electrons are negatively charged, so this comes out minus. So it has a negative formal charge. Then what we do is we add up all the formal charges. When we add up all the formal charges, we get something called the net charge. The net charge is the sum of the formal charges, and the net charge is minus this. So this would be the Lewis structure for bicarbonate. Now, we had a choice. You know, I picked this left oxygen. This is generated structure 1 here. Rather than picking this left oxygen, I could pick this top oxygen here and drop lone pair here and leave this one here. This would be structure 2. And so I'd do 1 or 2 for, and so I'll have the top oxygen sacrifice the lone pair. The left one doesn't have to. We end up with a structure that looks like this. Now, normally we don't show the non-zero formal charges. I mean, actually, normally we don't show the 0 formal charges. Normally we show the non-zero formal charges. So, can you tell me what the formal charge is for this oxygen is? Formal charge of this oxygen? Yeah, it's got 2, 4, 6, 7, so that's minus. This carbon? 0. This oxygen? 0. This oxygen? 0. The hydrogen? 0. And so when we add up all the formal charges, we have a net -1 charge on the ion. So this is the net charge over here. This is the formal charge here. This would be structure 2. And then structure 3 would be, well, we have 3 oxygens, so we had 3 choices for making the double bond. So this would be structure 3 if I pick the right oxygen to be the double bond. So if I did that, then I'd get this. Something like that. This would be the third possibility. What are the formal charges here? How about this oxygen? Has 7 electrons, which means it's supposed to have 6, so it came out ahead 1 electron. This carbon? 0. This oxygen? Minus. This oxygen? This oxygen comes out plus. It has 5. 1, 2, 3, 4, 5. 5 electrons. It's supposed to have 6, so it's missing 1. So we're lacking 1 negative charge. It's going to make it positive. And this hydrogen? 0. And so we'll add up the formal charges to get the net charge. So -1, -2, +1 gives us -1 as our net charge. Now you look at these. What can you say about 1 and 2? 1 and 2 look very, very similar, don't they? In fact, 1 and 2 are the same, pretty much the same energy. In fact, 1 and 2 are pretty much the same structure. Do you see that they're the same structure? But they're different. In a way, they're the same. In another way, they're different. They're same in the sense that, okay, that carbon has 1 double bonded oxygen and 2 single bonded. Layout looks very similar. They're the same in that way, but they're different in which oxygen. I have 2 choices for oxygen. I can pick the top one or the left one. Structure number 3, however, looks different, doesn't it? Structure number 3 looks different. And structure number 3 is unstable compared to 1 and 2. You know, what makes it unstable? Well, what makes it unstable is this. Let's say 1 oxygen here. Well, we got a negative charge. We can't help but having a negative charge because we have an extra electron. So the negative charge is going to go somewhere. And so let's say this oxygen gets a negative charge. Well, that means what's happening here with these 2 oxygens. This oxygen is gaining an electron, this oxygen is losing an electron. So if you have a tug of war between 2 oxygens, does one oxygen win and the other oxygen lose? It's a tug of war between 2 oxygens. You think, oh, well, oxygen versus oxygen, it should come out as a tie. This one isn't. This one we have a winner and we have a loser. Well, that's not stable. And so it turns out that this structure isn't as stable as the other 2. Now, all of these are showing differences in bonding. For example, oxygen typically forms 2 bonds. And so that's normally what we see, 2 bonds, like this oxygen, double bond, or this oxygen, 2 single bonds. 2 bonds here, 2 bonds here. But sometimes oxygen can form 1 bond. If oxygen forms 1 bond, then it has a negative charge. Or sometimes oxygen can form 3 bonds. If oxygen has 3 bonds, like this, 1 double and 1 single, double plus a single gives us 3 bonds altogether. That gives a positive charge. And so this 2 is just typical that it could be 1, 2, or 3 bonds. All right, this structure is not stable. The other 2 are. And so these are called resonance forms. Resonance forms are just, it's pretty much the same structure. It's just different ways of making it. You know, what we have to do is we have to fix the atoms in position. We don't move the atoms. We just see, you know, how can the electron be arranged, keeping the atoms in place. So we didn't touch the atoms, we just see, well, the electrons can You know, there could be a double bond here, or there could be a double bond there. Those are our resonance forms. So we end up with 2 resonance forms for this. Carbonic acid would have a hydrogen here. Let's try carbonate. Draw the Lewis structure for carbonate.